Welcome back to ECE 207. Today we have a couple of goals. The first is to work a power factor correction example, and the second goal is to introduce three-phase balanced power and what that means, and look at actually defining some of the terms like phase voltages and line voltages. Let's begin by returning to an example that we had talked about in the previous session, and we will basically start this example over. This is a power factor correction. The circuit is indicated here. What we want to do is we're given a single load S1. We now want to attach a second load to load 1 in an attempt to correct the power factor or change the power factor or improve it. In this case, make it closer to 1, put the power factor of the total combination of S1 and S2 to a value of 0.95 lagging. That may not make any sense until I tell you where we're starting. We're actually starting with S1 being more of a lagging system. It consumes 50 kilowatts of average power, and the power factor for load number 1 is 0.8 lagging. We want to introduce S2, a second load, put that in parallel with the first load, and select the impedance of S2 such that we correct the power factor a little bit. We move it from 0.8 to a value of 0.95 lagging. Once we found that, we can actually then determine a capacitor value to achieve the power factor total that produces this 0.95 lagging behavior. We're given then in this circuit S1, which is an average power of 50 kilowatts. We can call that P sub 1. We're also told that the power factor of load 1 is 0.8 lagging. We want to now find S sub 2 to achieve a 0.95 lagging behavior when we combine loads S1 and S2, or the total load should experience a 0.95 lagging power factor. If we look at what we have in very general terms, let's just sort of sketch a picture of what we are talking about. We are starting with a system that has a real power P1 equaling 50 kilowatts. And the real power, or the average power, is the horizontal direction in our power triangle. We are also told that we have a power factor of 0.8 lagging. That means that we are actually having an angle, and we'll just derive that in a minute, but for now we have an angle that's positive, or we have an inductive load, and we have some Q1, but we're not given that information explicitly. Really what we were given is indirectly we are given theta 1, and we also can then determine the apparent power, or the magnitude of the complex power S1, where S1 is P1 plus JQ1, and Q1 is some value determined by the power factor that was given, which we then can find theta 1 from. What we want to do is actually move the hypotenuse closer to just a straight line, horizontal line, and in this case what we are wanting to do is change the power factor by introducing a capacitive load to pull this down. So we want to now move in this direction by some amount Q sub t, so that the overall reactive component of our total system we want to do then is find this resulting power triangle, which we are calling having a reactive part of Q sub t. The real part of the total will actually not change. We don't want to absorb any more real power, and then this apparent power is S sub t. What we've been told indirectly by the power factor total, we've been told theta sub t. This is now the picture that we can keep in mind as we work through this problem. Let's now find Q sub 2, which will then allow us to find Q total. And actually, we're going to find Q total from theta sub t. That will allow us to find Q sub t. And once we've found Q sub t, we can find the capacitor that we want. So let's do that particular task. S1, or load 1, was given to us in terms of P1 and a power factor. We were given the following. We were told P1 was 50 kilowatts. We were told we had a power factor for load 1 of 0.8 lagging. That now allows us to find theta 1 by finding the inverse cosine of power factor 1. And because it's lagging, we have this positive sign, and the inverse cosine of 0.8 is 36.87 degrees. This is the given information that we were told. The picture then associated with that, now we know what that angle actually is. We have a hypotenuse, we have the real part. Here is P1, 50 kilowatts. We now know what this angle is, theta 1. That's 36.87. We can now actually determine from trigonometry what Q1 is, and we can also find what S1 is in terms of the magnitude. We know the angle is at an angle of 36.87. So if we just want the length of the hypotenuse, that's the apparent power, S sub 1. We have the hypotenuse as what's called the apparent power, or the product of the voltage and current in RMS units. We know our expression. The average power is the apparent power times the cosine of theta 1, or times the power factor of load 1. What we know is P1, we know PF1. That allows us now to compute the apparent power, which is P1 divided by power factor 1, which was 0.8, or the apparent power is now 50K over 0.8, and that becomes 62,500 volt amperes. That's now the length of a hypotenuse. We know the angle. That allows us now to solve for Q1. Q1 is simply the hypotenuse times the sine of theta 1, and theta 1 was 36.87. The magnitude, or the apparent power, was 62,500, or we now have for Q1, that's 37,500 volt amperes reactive. Now we know all of the different pieces to the triangle for load 1. We now have the complex power triangle for load 1. Let's now consider load 2, which has a complex power, which we can define as S sub 2. And in general, for a general load, S2 consists of some real power and some reactive power. Again, we can think of this triangle as being some real part P sub 2, some imaginary part Q sub 2, and the apparent power S sub 2 at a given angle theta sub 2. But in this problem, we're trying to do a power factor correction, and because of that, we're really not wanting to consume any more power. So we do not want to consume any more real power. What that means is we actually want P sub 2 to remain equal to 0, or to be 0. And the way that I've sketched that power triangle is maybe misleading. We actually want Q sub 2 to be negative because we want to take away from Q sub 1 and make the reactive piece of the overall combination of load 1 and load 2 smaller. What we want to do is we want to now find S2, but since P2 is 0, we're really wanting to find Q sub 2, and we want to find that in order to make Q sub T, which is the sum of Q sub 1 and Q sub 2. We want to make Q sub T smaller than what we started with, which was Q sub 1. We're actually given the information concerning how small we want to make Q sub 2 indirectly. The request was to end up with a power factor of 0.95. And that now allows us to solve for the total angle, or the combination of load 1 and load 2's angle. That's the inverse cosine of 0.95. And that's then 18.19, and the angle is lagging, so we're not coming all the way back through 0 and going negative. Our picture is what we had described before. Again, we have, beginning with P1, Q1, and S1. Also, this theta 1 of 36.87 degrees. Now what we want to do is we want to introduce a Q sub 2 such that we end up with the sum of Q1 and Q2 giving it, Q1 and Q sub 2, their sum gives us Q sub T. And we're not going to change the amount of the real power or the average power. P1 stays the same. And we now have S sub T, whose length is this hypotenuse length, and theta sub T we just determined to be 18.19 degrees. Let's now compute Q sub T, and from that obtain Q sub 2. What we know is that the total real power, or the total average power, is P1 plus P sub 2, but because we don't want our introduced load to consume any more average power, P sub 2 is 0, giving us P sub total is just the real power that we started with. That now allows us to say that we know P total, that's just this guy. We don't know what S sub t is, but we do know theta sub t. That was given indirectly by this specification on the total power factor. We now know power factor total. We know P sub t. Now we can actually solve for the apparent power of the total combination of loads 1 and load 2. That's PT over PF total, or that's 50,000 divided by 0.95, or that's now 52,632 volt amperes. We can now use that to find or break this into its rectangular components. We now know S sub t is P sub t plus J Q sub t, where P sub t was given and Q sub t is S sub t sine of theta sub t. If we compute 52,632 times the sine of 18.19 degrees, we will find that that's 16,430, and that's my total complex power for the combination of loads 1 and load 2. That's what we want to give us this power factor total of 0.95. Now, since Q sub t is the sum of Q1 and Q sub 2, we now have a way of finding or computing Q sub 2. Q sub t was 16,430. Q sub 1 we found was 37,500, and now the only unknown quantity in that equation is Q sub 2. We can solve for that, and now Q sub 2 is 16,430 minus 37,500, or that's a negative 21,070, and that's reactive power, or volt amperes reactive. That's now the S2 that we need. Is this J Q sub 2, which is minus J 21,070, and that we could call volt amperes, where P sub 2 is 0. That's now the way of finding the load. If somebody just said find S sub 2 to achieve a power factor total of 0.95 lagging, that would be the answer. That's now what we were saying was part A. Part B was saying, okay, if we know that that's the complex power of load 2, what is the actual impedance of load 2, or what is Z sub 2? And we know that V sub 2 is equal to Z sub 2 times I sub 2. That's just Ohm's law in the complex expression, or in the phasor form. S2, again, was J Q sub 2, which is minus J 21,070. And we can relate several formula or derive several formulas. All we are told now is S sub 2, and we were given back in the original problem description, we were given the voltage across those two loads. It was 230 volts RMS. That's now going to allow us to find the information that we need. V sub 2 is 230 at 0 degrees, and that's an RMS voltage. And we can now play with what we know. We know that the complex power is the product of the phasor voltage in RMS units times the conjugate of the current in RMS units. We can write the current in terms of voltage by Ohm's law. That now allows us to say that we have V sub 2 times V sub 2 conjugate over Z sub 2 conjugate, if we conjugate both terms in that parenthetical equation. But what do we know happens when we take a complex number by its conjugate? We simply find the magnitude squared of that quantity all over Z sub 2 conjugate, and that's now equal to S sub 2 bar. We could use that then to find Z sub 2. S sub 2 was this minus J 21,070, and that's equal to 230 squared over Z sub 2 complex conjugate. Or we now have that Z sub 2 complex conjugate is 230 squared over minus J 21,070. We can now simply plug in these numbers, and we find that we now have 230 squared divided by 21,070 will give us 2.51, and that's now over this minus J. We can always multiply by 1, which is J over J. In the denominator, we have J squared, which is actually minus 1 times a minus 1, or that now ends up being a minus 1 times a minus 1, which gives us 1, and we have Z sub 2 conjugate is J 2.51. That's the conjugate of Z sub 2, and it's not hard then to find the conjugate of a complex number. We simply change the sign of the imaginary part, and we now know that the the impedance of load number 2 is minus J 2.51. What we want to do is find the capacitance or inductance of that particular impedance. We are now in sinusoidal steady state. In order to find an impedance that's negative, that can actually be determined or realized by a capacitor, since the capacitor impedance is 1 over J omega C. Again, we could, if we wanted to, multiply by 1, and that now has J times J in the denominator, but J squared is minus 1, or we now have minus J times 1 over omega C. That now says that 2.51 is going to give us 1 over omega C, and we can now solve for C, since we can find omega if we know where we're operating this particular system. In the United States, for example, we have a line frequency of 60 hertz. That means that our angular frequency in radians per second is 2 pi times f, or 120 pi, or if we do the math, that's now 377 radians per second. That's omega. If that's now omega, we have everything we need. We now have this minus J 2.51 is equal to a minus J times 1 over 377 times C. The minus J's cancel, as I had indicated before, and now we have C is equal to 1 over 377 divided by 2.51. Or that becomes 0.00106 farads, and now we know what the capacitor is. The capacitor, if we move over, let's say move the decimal place 6 places to the right, we could express that in terms of microfarads. Here is, microfarads. Here is now 3 gives us 1.06 millifarads. If we go another 3, that will give us 1,060 microfarads. And that's now the capacitor value for load 2 if we're operating this in the United States with a line frequency of 60 hertz.